for sets, we always have this distributivity between intersection and union, whereas that is not the case here. Okay? Simple example. Okay. I'm taking in R2. Well, there will be only about complex Hilbert spaces, but for example, it's okay. I'll take real Hilbert space. So R2, you take 3 subspaces, that means lines passing through the origin. So one-dimensional subspaces, none of them orthogonal to other. Okay, just 3 generic ones, none orthogonal to other. So some P1, P2, P2. So the projection onto these subspaces are my P1, P2, P3. Okay. So if you do that, if you take any 2 of them, okay, Pi, and if you take the projection onto the intersection is just 0 subspace. So Pi mean Pj is just 0. Okay, for every I not equal to j. Okay, for this P of that. Okay, because the intersection is just the 0 subspace. Whereas if you take the union, so since I have taken them, we not same, distinct. So the union here, that would span the whole R2. So the union would be identity, right? It would be projection onto identity. Pi, Pj is just identity for every I not equal to j. So that happens. So any 3 projections here, I don't take them same and distinct, and I also okay. So now what happens? Now if you do that, so P1 minimum, P2 max, P3. So like here the left hand side, P2 max, P3 is identity, right? If you take minimum of that with P1, so that gives you P1. So on the left hand side here you get P1. Whereas this minimum is 0, this minimum is 0, so the maximum of that is 0. Okay? So that this is what you get in the left hand side, you get P1, and here you get 0. So they are not same. Okay? Similar thing for this one. P2 min P3 is 0. If you take max with that, you get P1. Whereas here you get identity, here you get identity, and the intersection of that you get identity, right? So
also done it on C2, right?
yeah, I can't draw it. I can't draw C2, but yeah, it is the same thing. In general, it's okay. So that is the main difference. So that leads to many complications. Okay, so you immediately see that the model is different. Okay, is different from the classical model for the events. Okay. So next, we want to assign probabilities. Okay. Yes, I can forget this. Have this omega and mu. Okay? So what is mu? So mu is a measure. So it is a mapping from F to R. Mu of the empty set should be 0. Mu of the whole set should be 1. Probability measure. And mu of A complement should be 1 minus mu of A. And mu of A union B equals mu of A plus mu of B if A intersected with B empty, because A and B are in F. And you also have countable additivity. Belongs to F. So the mu is sort of a probability. Probability that something from omega occurs is 1. That is the whole space. Always something has to occur from omega. Omega is considered the set of all possible outcomes. So something has to occur, that's why that is 1, and for this it is 0. And for if you have the probability of A occurring as some number, probability of A not occurring should be 1 minus that. That is what this is. And if I have disjoint things, then the probability of either A or B occurring should be the sum. Okay. So this is the usual measure theory axioms what you have. Okay. The similar thing I would like to have now on projections. Okay. So
what is the letter there? The measure is it rho or?
That is rho. Okay. So that I will come to later. So I would like to have I will explain what is that rho. But to begin with, I would like to have a probability measure. Okay. On P of H, right? I would like to have something similar. So I would like to have a mu, so that mu of 0 is 0, mu of identity is 1. I will just imitate. So mu of P per should be 1 minus mu of P. Okay. I would like to have this kind of things. Mu of P1 plus P2 is mu of P1 plus mu of P2 if P1 is orthogonal to P2. Okay, which is same as saying P1 means P2 equal to 0. Okay. So if you have two projections P1 and P2, P1 plus P2 is in general not a projection. It's a projection if and only if the intersection of the ranges is 0. Okay, P1 means P2 is 0. Then I would like this to add up. And the same thing in general. Okay, mu of summation Pj. This is will be the ranges would all be orthogonal, so it will be a direct sum. Okay, the subspaces of ranges of Pj's will all have to be mutually orthogonal.
Yes.
So this should be mu of I orthogonal to Pj, whereas I is not equal. This is what I am going to have. Okay, here is an example. Take some Hilbert space. You can take separate finite dimensional. No problem. So fix a unit vector. Fix u belonging to H with norm of u equal to 1. So define mu on the projections by mu of P equals, you apply it on a vector, on this vector u and take inner product with u. Okay, u P u. Mu of P is defined as this, P of u inner product with u. Okay, so if you are thinking of say Cn, okay, H is Cn, I may take u as the, say, the first basis vector. Any unit vector will do. So then what this is giving you is you apply, so this is the basis vector, say E1. So apply P on E1, take inner product with E1. So that gives you just the 1 entry of P. Right?
Yeah. Another problem.
Yeah.
When you write P1 orthogonal to P2, you mean their ranges are orthogonal, right?
Yes, yes.
But two subspaces may have trivial intersection without being orthogonal. So
Yes, yes, yes.
how are those two things the same?
You mean orthogonal? Yeah, that's the question.
Yeah, no, this is
You mean
not.
orthogonal?
This is not. Sorry. Yeah, you are right. Yeah, this is not. This is not. This is not the same. Yeah. I want this. What I want is this. So yeah, you are right. Huh? So it's very right. That is not the case. It's not that P1 mu. Okay. Yeah. That we had this example. Two lines which are not orthogonal, but the intersection is that can happen. Okay, so that is much weaker. What I would like to have is this. Yeah, okay. So this is what we are putting. I want to say that this satisfies all those conditions. Okay? Mu of there is one thing which is clear from here. The mu should always be between 0 and 1. Right? So, did I mention that? Is it? Let me follow from here, right?
Mu of identity is 1.
Yeah?
Mu of identity is 1.
1.
And the sum should be
Well, yeah, but I didn't say anywhere it should be non-negative, right? So mu should be from P of H to R plus. If I say that, then anywhere. See, this is always non-negative because P is a projection. So this is also equal to u p square u, and I can take one p to the other side, so it becomes pu because p star is also p, so this is greater than or equal to 0. So this is always non-negative. Okay. Any projection is positive. So mu is non-negative, and mu of 0 is 0, of course, and mu of identity